Okay, let's start. Welcome everybody. So today we are gonna introduce to IFT-Unesp one of our new members, Martino Stefanini, who just joined ICTP-SAIFR and IFT-Unesp when? 2 weeks ago, 3 weeks ago, something like that?
1 month ago.
Actually. 1 month ago, okay. Okay, he's already a veteran. So Martino is an expert in quantum systems, quantum many-body systems, out of equilibrium, things like that. He got his PhD in CISA, then he did one postdoc in Mainz, in Germany, and then he decided to join us here. So as I said, he's an expert in quantum many-body physics and techniques to study them, and today's talk is going to be about that. The title is going to be Open Quantum Systems and the Lindblad Master Equation. Martino, the floor is yours.
Thank you, Dario. So yes, hi everyone, Martino. As Dario said, I've been working on mostly dynamics of quantum systems, especially out of equilibrium, and open quantum systems. So I guess that for introducing myself, this colloquium on open quantum systems and the main tool to study them, which is the Lindblad Master Equation, should be a good start. So what is an open quantum system? I am Italian, so I will think of food. Boiling pasta. So this is definitely an open system. There is an external drive. We are pumping energy into the pot with a stove, so heat is entering into the system, but also it is being dissipated outside of the system, so there's thermal radiation coming out of the pot, there is convection bringing out heat, and there's exchange of matter in the form of vapor of water steam leaving the pot. And of course, the whole point of bringing this system out of equilibrium is to get an interesting steady state, which is cooked pasta. Okay, of course, this is a little bit of a tongue-in-cheek example. Of course, we don't have to, I mean, this is definitely a quantum system unless you have wild ideas on how quantum mechanics works. So this thing should obey a Schrödinger equation. Of course, it's in a regime in which quantum effects are not usually present. I don't have to care about superposition or entanglement when I cook pasta. So maybe a more conventional open quantum system in which quantum mechanics plays really a role is spontaneous emission, which is probably one of the very oldest, the oldest open quantum systems that have been studied. There's this seminal paper by Wigner and Weisskopf from 1930, so quantum mechanics was just 4 or 5 years old. So spontaneous emission, so when we learn to solve the Schrödinger equation for the hydrogen atom, we actually know from the start that all excited states are actually unstable in nature, and the reason is electrons and the protons are charged, they constantly interact with the electromagnetic field. And this makes the hydrogen atom, or any atom, an open quantum system. And if you excite the electron to a higher level, let's say a p state here, this state is going to decay to a more stable state, a ground state, by emitting one photon in the vacuum. So this is a cartoon, but this is a nice actual picture of spontaneous emission in a lab. So this is a picture taken from by Emanuel Bloch's group in Munich. And these dots are rubidium atoms suspended in an optical lattice. And they are imaged with an actual microscope by exploiting spontaneous emission. So they are constantly excited for a certain period of time with a laser, and then they emit photon going back to the ground state. So more in general, open quantum systems have this structure. We are interested in a certain subset of degrees of freedom, let's say our atom or our experiments of whatever type. And this system is embedded in a larger system, often infinite, like the electromagnetic field. And this larger subsystem is the environment, has usually lots of degrees of freedom. And the coupling between them is usually fair to consider it weak. This is almost a conceptual point. If the interaction is too strong, then it becomes ambiguous to define what is a system, of course. It would be completely mingling with the environment. So this, if you think a little bit about it, this setup is the setup of thermodynamics. So if you take the 5th book of Landauer-Lifshitz and look on how you derive the Gibbs ensemble, is exactly like this. There's a small subsystem of a larger subsystem, and of course, you derive the Gibbs ensemble by assuming thermal equilibrium, maximum entropy, and so on. But this already tells us that open quantum systems will show irreversible behavior, because thermodynamics is going to play a role here. Irreversible behavior means that entropy is going to be produced, particles and energy is going to be exchanged, and so on. And this already points to a fundamental difference between open and closed quantum systems. In a closed quantum system, or better, isolated quantum system, obeying the Schrödinger equation, the dynamics is essentially rotation in the Hilbert space. If we were able to visualize a Hilbert space with 1,000 of dimensions, we would see something like this. Open quantum system dynamics, instead, is irreversible, meaning it has a direction. There's an arrow of time. And generally, you start from many possible states, but you always end up in a stationary state, at which point, essentially, the dynamics stops. Of course, this happens on certain time scales and so on. But this is probably the fundamental difference between open and closed quantum systems, or open and closed systems also in general. So why studying these systems? Well, the obvious answer is that they exist. Virtually every system you can think of, or you can find in a lab, is open, except maybe the universe. This is, metaphysics. So, and in any environment, we're going to see the effects of noise. Most often, noise from the environment is not welcome. For instance, we want to try to study some out-of equilibrium dynamics, but the system, the environment, which might be, again, the electromagnetic field, commonly the apparatus or whatever, is going to thermalize the system, and unless you want to study thermal physics, that's probably not what you want to see. But there's also a subtle point, which is the fact that environments generally provide, except for decay, let's say thermalization, they provide dephasing or decoherence, meaning they act a little bit as measurement devices, and the fundamental things that makes quantum mechanics quantum, which is superposition or the ability of producing interference, depend on the fact that you have definite phase relationships between the components of a wave function. And if you put an environment in the game, the environment is going to measure the phase in quotes and destroy the ability of producing interference. So these things of, let's say, dissipation as noise have two aspects. One, practical. We want to do experiments in which we want to probe quantum mechanics, so we need to learn how to deal with this and possibly to minimize these unwanted effects. Also, as a fundamental aspect, so this mechanism of dephasing is one of the ingredients that makes classical physics emerge out of quantum physics. And the person who studied this point most of all is Wojciech Zurek. Then, I'm possibly a little bit repeating myself, but let's say the fundamentally interesting thing about open quantum systems is that they are different from unitary dynamics. The thermalization is not necessarily the outcome of open quantum systems. If you wait long enough, it usually is, but let's say there you can have intermediate situations in which you can actually bring the system out of equilibrium, keep it there in a non-thermal state. And this is also the idea of using dissipation as a resource. Again, beginning with a somewhat trivial example is cooling. When you want to cool your sample to 1 nanokelvin because you want to see Bose-Einstein condensation, what you do is to put the system in a refrigerator and use the refrigerator, which is the environment, as a way of turning down the temperature. The outcome is a thermal state, but it's an interesting thermal state which has quantum properties that we want to study. There is also a more sophisticated way of using the environment and the fact that there is an arrow of time, so we can drive the system towards a state. And it's the business of engineering the environment, of having the right environment and right driving of the system that brings the state of the system to a target state which is non-thermal, so outside of the scope of common thermodynamics. And that might have interesting properties. It's maybe highly entangled for quantum computing, or has topological order, or I mean, you name it. The sky's the limit in this case. But there's a lot of people doing this kind of stuff, like the bath engineering and so on. So this is probably a reminder for, I think, most of you, so on how to treat open quantum systems. And this is a little bit the, let's say, quantum information / quantum optics point of view on open quantum systems. So the whole point is the environment is way too big to be followed. Let's say, you cannot write down and solve the Schrödinger equation for the full system plus environment super system. So, and maybe we don't even know the details of the environment. So we would like a description which removes the necessity to track the environment.
Yes. So in this interaction with the environment, is it included? It will be touched, the interaction with the measurement apparatus? I mean, the environment can also be the experimenter that does the measure? Or is it a different issue?
Let's say, throughout all this talk, I won't deal with measurements.
Okay. That's what.
In principle, you can add, yes, you can, of course, add a measurement on the environment, and you will get weak measurements, which can be transformed into master equations like this, but then, I mean, it's a non-unitary evolution from the start at that point, because measurement is, of course, not unitary, and you get a different description. But in principle, you can apply the same reasoning.
Okay, but that's not what you're aiming to.
No. When I say that the environment is kind of measuring, it's I mean, at the very beginning, people were hoping that actually these kind of things would explain measurement. Of course, it cannot. Measurement is still, you know, projective, and there is no way of getting a unitary evolution performing a projection. So it shares some aspects with the act of measurement, like dephasing. That's also one thing, but let's say it's only half the story, not the full story. So as I was saying, the quantum optics, quantum info point of view is to describe the system through its density matrix. The definition is this one, so you can always think that if you include enough degrees of freedom, the full system plus environment super system or universe is described by pure state. You form the projector over this pure state, and you trace this projector over the environmental degrees of freedom. The outcome is an operator on the Hilbert space of the system, and this operator contains all the information that you need to know to compute any observable of the system. You just compute this trace here. This operator has 3 important properties. It is Hermitian. It is positive semi-definite, meaning that its eigenvalues are never negative. And it's of trace 1. Taken all together, this means that its eigenvalues are probabilities. So they're positive numbers that sum to 1. And the fact that these are probabilities is, this normalization to 1 means that, as I said, we are exhausting, this object exhausts all the information that we can have according to quantum mechanics on all possible measurements that we can perform on the system. And with this object, let's say, from this perspective, what are the questions that we would like to ask? The most trivial question is a static question. What is the steady state of the system? What is the final state of the dynamics? Is it unique? Does it have interesting properties from a fundamental or applied point of view, and so on and so forth? Then the next question in complexity is, how is this state approached in time? So what is the relaxation of the system? And the common approach is try and derive some form of master equation, so an equation of motion for the density matrix of the system. Formally, we know actually the answer to this. We can write down the full evolution, the full unitary evolution of the full system plus environment, density matrix, and trace out the environment. Of course, by the same token as before, this is only formal. We can derive some mathematical properties out of it, but it's useless to make actual computation because it's very hard to track the environment. So can we approximate it or simplify it into something useful? So I'm going to give you a quick and dirty derivation of a master equation. It's going to be it's going to turn out to be let's say the correct one under some circumstances. So a very old idea about decay is to mimic decay by making the energies of the system, the eigenenergies of the system, slightly imaginary. So you have your unitary evolution of an eigenstate, and then you make this eigenstate, you endow this eigenstate with a negative imaginary part, and you will get decay. Equivalently, we can think of switching to an effective Hamiltonian, which has an anti-Hermitian component. This was, I think, probably this was first used in this approach to describe scatterings of nuclei. So we want a decay, so this operator gamma must be positive semi-definite, otherwise this object is going to have the wrong sign and this thing will blow up, so this would not be a decay. Now, you can always write a positive operator as a product of this kind for some L. This decomposition is not unique, but this is not a problem in what I want to say. And then you can write down the master equation for this process, and you get this commutator term, which is the usual unitary dynamics, and then this anti-commutator, which embodies decay. Now, the problem is that if you compute the evolution of the trace of this object, this trace diminishes in time. Now, I said that the fact that the trace is 1, it means that we are keeping track of all the information that we have in the system. If the trace goes down, it means that this system is not compatible with, this description is not compatible with quantum mechanics. We're going to have measurements with undefined outcome. So a little, fiddling around with the properties of the trace, you find that if you add this term, you can actually compensate for the loss of probability. So we can write down this master equation, which at least conserves probability, as an attempt to describe decay. Turns out that
let's see. So actually, this gives a prescription whenever you have a non-Hermitian Hamiltonian, you take the, let's say, the non-Hermitian part, you can always write like L dagger L, and then you have the prescription to complete it. This is true for every...
Yes, yes, I would say so, yes.
Okay.
It's a quick and dirty derivation. It's very non-rigorous, but it gives you the right answer.
Satisfy, let's say, satisfy the rules of the game, so
Yes,
why not?
yes.
Okay.
But it turns out that essentially...
You know why I'm asking? Because there are people that just study the non-Hermitian part, and I'm wondering, so this say that you can always complete the non-Hermitian part to a part that at least preserve probability?
Yes.
Okay. And the positivity is also...
The positivity
included?
comes from writing the non-Hermitian part as a product of this form.
Okay, yes.
So this is the more general version of the equation that I wrote before with multiple decay channels. And so each decay channel is defined by this L operator. It's called jump operator. There is no particular restriction of which kind of operator it is. Could be Hermitian, non-Hermitian, unitary, you name it. And each defines a dissipative channel, and the rate of this process are these gammas, which must be positive, which is the only constraint that we have. And it turns out that this equation has special properties. It not only conserves probability, but conserves also the positivity of the density matrix, which is a crucial point. We don't want to have negative probabilities. So actually, it has a technical property which is called complete positivity, but it's, let's say, a technical point, which is important, but conceptually is more or less the same as positivity. So whatever, as long as you put as an input an initial state, which is physical, trace 1 and positive, you will get as an output at any time a physical state. And these people that I forgot to mention before, Gorini, Kosakowski, Sudarshan, Lindblad, earned the right to have an equation named after them because they proved that this form of a master equation is the most general master equation that conserves physicality of the density matrix with the extra constraint that it must be a Markovian master equation. Markovian meaning that the rate of change of the density matrix depends on the present state of the density matrix and on its history. Because in general, when you have a subsystem of a bigger system, you would have probably generally an integral over time here and a sum over, the system has memory essentially of the previous states. So this is the simplest master equation that's consistent with quantum mechanics and doesn't have memory.
Do you have there is such a general result when you give up Markovianity, or I mean, there is a generalization of this that.
Well, essentially, you take the formal expression trace of over the environment of stuff, and you can basically prove that it's not divisible, which is the property of Markovianity in a nutshell. Yes. Yes, at this point, it's formal properties of the Lindblad master equation. That's a very important point, but I'll discuss it later.
Okay, and can you just say some words about this index A? What is this A exactly?
It's integer index, and it runs, let's say you can meaningfully distinguish up to d squared minus 1 jump operators where d is the dimension of the Hilbert space. More than these, they are become redundant essentially. So, other questions? No.
Maybe yes. I don't remember if the previous or 2 slides ago, you showed us that all the let's say all the decay part can be written as L dagger L.
Yes.
Now you are so you are treating various decays, various.
Yes.
Okay.
Yes.
Okay.
Yes. Now, the big advantage of having an equation of this form, it's that thanks to the property of Markovianity, it's an ordinary linear differential equation, so we know how to solve it, at least in principle, and we can understand which kind of physics, what kind of physics is described. So, in a very formal manner, you can write the equation as this. This is a linear operator that's called Lindbladian or Liouvillean. It's a super operator, so an operator that acts on other operators. If you can think it as a tensor if you wish. But regardless, it's linear. So to solve a linear equation, you just need to find the eigenvalues and eigenstates of the linear operator. The difference between with the unitary dynamics, with the Schrödinger equation, is that this linear operator is generally non-Hermitian. So it has a certain set of complex eigenvalues, lambda, but it has two sets of eigenstates, the right and the left eigenstates. This is, again, a technicality. And the outcome is that the evolution, at least formally, of any Lindblad-Master equation is going to be a certain set of sum over a certain set of states with a set of coefficients which depend on initial conditions times e to the lambda mu t for the various rates. These lambdas are complex numbers, so there's generally oscillations and decay at the same time. But this specific form of the Lindbladian guarantees two things which are important. One, the real part of these eigenvalues, it's always negative or zero, which means this object never blows up in time. And also, there is at least always one stationary state, or zero, with a vanishing eigenvalues. Putting all things together, it means that, in general, you can expect that the density matrix is going to relax exponentially to a steady state. This is the kind of physics that you can expect to find. You can have variation of this. Yes?
You never find, let's say, a family of steady state in which, let's say, you have a lambda that is strictly imaginary, and so you start to rotate, let's say...
No, you can have it, yes.
Ah, okay.
Well, Hamiltonian dynamics is like that.
Exactly. So yeah,
no, of course, yes.
Okay. So let's say your quote with R0 with lambda 0 equal to 0 is more like a real part of lambda 0 is equal to 0, but can be an imaginary part that keep rotating.
So you need for sure you need an Hamiltonian with, so that's one possibility. The typical situation is that you relax, at least for a finite system. You can have surprises if you have a many-body system in the thermodynamic limit. So that's why I put this. Could be non-exponential, could be that this thing actually never relaxes. But the usual expectation, I guess that if you have a Lindbladian, let's say the exception is that, of course, if all the gammas are zero, all the lambdas are going to be real. Are going to be imaginary, so there's never be a relaxation. Mm-hmm. So this theorem applies if you have a dissipator. Okay. Yes.
In which you're saying that this dynamics describes exponential relaxation to a stationary state.
Yes.
It means that this method, these Lindblad equations, will not allow for revivals. Is that so or no?
Well, you have revivals. You can have revivals, but they're usually, they are accompanied by a relaxation. So you can see oscillations, but they will eventually decay. So of course, if you have a finite system, information will travel and bounce off the edges of the system. So you can have revivals of this kind. But thanks to the dissipation, as long as the dissipation is finite, is there, you will kill everything. Because let's say in the most trivial scenario, this is really describing thermalization. So you expect in the end to get your Gibbs state without any particular problem. an example, spontaneous emission, the second thing that I've shown. So we have our atom with a certain set of excited states, and we're going to just single out ground state and one excited state, which is connected by the interaction with the electromagnetic field. Let's say it could be an S and a P state. This, of course, maps to a spin. So we can use the spin language. Spin language is usually used in this case. The jump operator, at least when the environment is a 0 temperature, it's just 1. It's the one that it's the sigma minus operator that brings you from excited to ground state, and you have this equation. Basically, you could guess that this is the form, but it turns out that, I mean, you can do the calculation and actually derive this form. And then you find a certain rate, which depends on the properties of the atom and fundamental constants. And the solution of this equation, you can find it by just taking matrix elements. You're going to find that there are just this equation, which is the equation for a 2x2 matrix, is actually equivalent. There are only 2 components which are truly independent, and you can solve for them. And you find this. This already has a certain amount of information. These objects quantify the quantumness of the state and decay with half of the rate. Then there is equilibration with the full rate, but eventually the system is going to go to the ground state on a time scale which is 1 over gamma. Yes.
Hey, and just a quick question. You said the eigenvalues, the lambdas are always negative, right? Something.
The real part is
okay.
Negative or at most 0.
Mm. So this means
it means that you can never have, I mean, these are essentially the eigenvalues. It means that the sign here is always minus, and this object can never blow up.
Sure. Because like, this makes sense for me if you're thinking of like cooling a system, but I could also want to describe like putting something on a highly energetic thermal bath.
Sure.
Could I also use?
Sure. For instance, in this case, if you imagine that you put your atom in an oven so that the electromagnetic field is at a finite temperature, you're going to have a second channel which looks like this, but with sigma minus and sigma plus swapped, and this will give you the final outcome is going to be a thermal state of an atom with an incoherent superposition of ground and excited, so a state which is Gibbs. But you will never, I mean, this thing is still essentially an exponential approach, but it's, maybe I can just, roughly speaking, you have some, I don't know, excited state as a function of time. At 0 temperature, you're going to have exponential relaxation because you go to the ground state. At finite temperature, you're just going to have a non-zero limit. So you shift the limit there. But if you work back the eigenvalues of the super operator, there's always going to be positive rates, meaning negative real parts. Because again, if you would have positive real parts, the result is always this.
Thank you.
So I'd like to ask, like in the solution you present, the diagonal terms decay with gamma, and the coherence of diagonal decay with gamma over 2. Is there a reason, like a physical reason for that? Is that the common solution?
I would say so this is often used as a rule of thumb. So in most cases, you solve the equation and you find that the decay of the coherences is slower and the rate is half of the diagonal term. So it's half of the relaxation. So the diagonal is relaxation, and the off-diagonal is dephasing. This is not an absolute truth. You can find system which violates this this relationship. So that the numerical factor, it's not necessarily 2 between the two rates. But at least in this case, it shouldn't be hard to see that the main constraint is that this object must be positive. The eigenvalues must be positive. I mean, the trace is 1 by definition, so that's not a problem. If you take the determinant, must be positive as well. And essentially, you get an e to the minus gamma t from this point, and then another e to the minus gamma t from this point. So if the decay were faster here, you would get, at some point, you would get negative eigenvalues. So at least in this case, you can argue that the point is you must keep the density matrix positive.
But I would say probably another way is that this thing that you said has to do with the 1/2
oh, yes,
in the chat.
Yes. Yes,
if you want, the first term is diagonal, the other is non-diagonal, and there is a factor 1/2 that creates.
Yes, I mean, at a simpler level, yes. The anticommutator is what gives you decay, and this 1/2 is exactly this 1/2, whereas this object is what is really bringing you from excited to ground state, so this is dominating the relaxation, so you get gamma, which is the coefficient in front of here.
Thanks.
So, is it physical of all of them? I've told you that this is the actual dynamics of any open quantum system. So, if you work a little bit on this, you will find that it's not in the Lindblad form. This is not Lindbladian dynamics. So it must mean that the equation that I've shown you is approximate. And indeed, this there's a pretty standard derivation of the equation based on perturbation theory in a smart way. And this will give you, and this is the, I got a question like this before. If you follow the derivation, you would have a specific form of HS and of the jump operators. So these are prescribed. If I give you the full system plus environment Hamiltonian, you will be able to write down which are these jump operators, and not arbitrary. However, this equation is very robust in the sense that, again, it always preserves the physical soundness of the solution. So many people use it essentially in a phenomenological way, in which you guess or choose the jump operators according to your physical intuition of what the environment is doing. If the environment is subtracting particles to your system, then the jump operators are going to be annihilation operators. If you have just dephasing, it's number operators, and the list goes on. This has some success as an approach. Essentially, the rates can be more or less estimated, a Fermi-Golden rule, or just fitted to experiments. But the good point of this is that you have an equation which is extremely flexible. You can adapt it to a wide range of circumstances, and indeed, these equations spread out of quantum optics to quantum info, modeling photosynthetic compounds, modern AMO physics, which means ultra-cold atoms, all sorts of quantum simulators, many-body physics, and even quantum field theory, black holes, heavy ion collisions, and so on and so forth. Of course, probably I won't have the time to give you the full spectrum of problems. This approach, it's often powerful and effective, but it's not without pitfalls. You can have dynamics which looks reasonable because it gives you a reasonable density matrix, but if you do not respect some properties of the jump operators, you're going to have a dynamic which is just mathematics. it does not correspond to any reasonable physical system. Indeed. So the basic challenges and of studying dynamics with the Lindblad master equation are, as I said, the very basic task is to find the steady state and maybe find a set of jumps and Hamiltonian that gives you a steady state which you want because of it has some interesting properties. Then we would like to solve for the full dynamics of this steady state, of dynamics of the approach to the steady state, or maybe a dynamics which doesn't have a steady state, as we discussed a little bit earlier. And the simplest method is essentially what I showed you before. You write down explicitly the equations, maybe on a computer, and you solve them. They are ordinary differential equations. There exist tons of routines which solve them without much effort. This is called exact diagonalization. The fundamental limit, as usual, is the number of equations you have. Pure states, so unitary dynamics, live in the Hilbert space, so it's a list of numbers. Density matrices are matrices, so they have the square of the number. So if the number of elements here is d, the dimension of the Hilbert space, the element here, the number of elements here is d squared. It's a little bit lower than that. There are relationships. Not all the elements are independent, but I mean the scaling is at 1. And this puts severe constraints. For instance, if you take a system which is just 10 spin 1/2 objects, let's say 10 two-level atoms, the dimension of the Hilbert space is about 1,000. But the dimension of the vector space in which the density matrices live, it's 1 million. So if you want to diagonalize the Hamiltonian as a matrix, it's 1,000 by 1,000, but the Liouvillean is 1 million by 1 million. So, 10 essentially doing exact diagonalization on 10 spins is usually already borderline on most computers. So how to work around this? One set of approaches could be said to just reduce the number of variables. So use symmetries or maybe the sparseness of the matrices to reduce the number of dimensions, or maybe you can have some smart ansatz for the density matrix so that you restrict the dynamics on some manifold that you can control. Simplest is probably mean field, so everything is factorized between the components of the system. Then there's matrix product states, tensor networks, very fancy stuff. A different method, which was very successful since the 90s, is so-called quantum trajectory methods. These are essentially, they work in the Hilbert space and not in the doubled Hilbert space of density matrices. And it's basically a way to sample the state of the system by simulating stochastic motion of a state in the Hilbert space. This is very efficient, but only works if the equation is in the Lindblad form. I'm saying this because there are other master equations, and you cannot do this trick for other master equations, which is one of the other big advantages of the Lindblad master equations. So you would like to have a Lindblad form if you want to play this game. Another possibility is actually complementary. So you use the equation for the state, but you actually look at observables. Simplest thing is so-called decumulant expansion, which means you write down the equations of motions for correlation functions. 2-point functions will depend on 3- and 4-point functions, and there's a hierarchy, an infinite hierarchy, and you truncate the hierarchy. This is usually simple, but it's often uncontrolled. Not always. It doesn't always work. Other methods are based on semiclassics in phase space. This go under the name of truncated Wigner approximation. It works when you have reason to believe that the system is close to a classical state, where classical depends on the system. Let's say you have a very big spin, or maybe bosons with high occupation. And it's, again, a stochastic approach in which you put back some quantum fluctuations around a classical solution. Finally, another recent development is, these people, Lucas Sieberer, Sebastian Dio, and Misha Buchholz, were able to rewrite the Lindblad master equation as a Keldysh path integral. So it's basically a field theory, and you can then import all your field theory methods to treat the Lindblad master equation. So randomization group, diagrammatics, saddle points, and so on and so forth. And of course, I mean, this is a very partial list, and it's, you know, you probably find other things. Probably these are some of the major approaches that you can find to treat Lindblad master equation. Now, oops, too much. So I don't think I have much time. Well, if you don't mind, I'll try to give you to speak of the derivation, actually, of the Lindblad equation from an Hamiltonian, which is the tricky part. So, as I said, the Lindblad master equation is in general approximate. To be fair, there are cases in which it is actually exact. For instance, if you are measuring the system and throwing away the results, you get exactly, the dynamics of the system is exactly given by an equation in the Lindblad form, but this is not unitary dynamics, it's measurements, so it's a bit different. Still, when you want to study and cool the quantum system in your experiments that's coupled to an environment, this is what you want to do. You want to derive it from an Hamiltonian.
Sorry,
yes?
I'm not sure I got. You are saying if you have a unitary evolution, but you measure the system and, let's say, you trace out in the sense that you average over the outcomes, let's say.
No
right?
environment, you just have the system.
Right.
You measure the system, you measure an observable of the system. Let's say maybe you have an environment. It's easier to do it if you have a weak measurement.
Okay.
So not necessarily projective,
sure,
but a weak measurement. So you measure, you get some result, but then you throw out the result, meaning that you make an average.
Yeah, exactly.
Over
in
the
that
results.
case, you are saying any Hamiltonian evolution will have a corresponding Lindblad, let's say, any Hamiltonian plus measurement will have an exact, let's say, mapping to a Lindblad.
So the evolution is, because the evolution is exactly in the Lindblad form, where the jump operator is the observable you're measuring.
Okay, but do you have a recipe that for the most general Hamiltonian and the most general thing, I can build the Lindblad, or in any case it's a piece of art and I need to be smart?
I'm not aware of any particular pitfalls. As I said, if you're measuring observable X, then you will have Lindblad master equation with jump operator X.
Okay, we need to talk later. I have a question in more details. Yeah, thanks.
Yes, but it works. I mean, the main point that it works is that measurements are Markovian. So the Lindblad master equation has basically been derived in quantum optics, and but it's spread outside of it, and essentially, speaking with people around, at some point we realized that people outside of quantum optics have not a very clear ideas about the limits of applicability of the Lindblad master equation. So, and now I'm doing some shameless self-advertising, along with my postdoc advisor, Jamil Marino, and colleagues. We wrote down a pedagogical review on this point, which is on arXiv. And let's say in the next few slides, I'll try to, I'm drawing on that review to give you a flavor of what are the limits and how is this equation derived. So the basic setup is this. We have system plus environment plus interaction, and we have a total Hamiltonian, so the total dynamics is unitary, and there's some small, in some sense, I will become clear later, small coupling constant between the two. Typical situation, we assume that the two parts are uncorrelated at time 0. It's a relatively innocuous assumption. Essentially, you think that you turn on the coupling at time 0 and let it evolve. And for simplicity, you can think of the simplest situation in which the environment is at equilibrium, thermal equilibrium. That makes the math a little bit simpler to follow, but it's not a requirement of Lindblad. The environment could be out of equilibrium. And again, for simplicity, we can think of the interaction as being a product of an operator A that acts on the system, an operator B that acts on the environment. You can always write down the most general interaction that you like as a sum of these kind of terms, but one term is easier to think of. An example, if you take a two-level atom in an electromagnetic field, the interaction is in this form. The operator A is sigma x, is the dipole operator for the atom, and the operator B is the electric field, which is, of course, it's expressed in terms of ladder operators for photons. Also, it's convenient to assume that the average of this B operator over the initial state is 0. Like, for instance, in this case, if you take the average of this operator over a thermal state of photons is going to be 0. This it is not a requirement, but it's a simplification for the aim of this talk. So all the information that we need is encoded in noise, which means correlation function of the B operator over the initial state. This correlation function usually is some decaying function of time, and in many cases you can recognize that there's a typical time scale over which the noise it becomes uncorrelated. And for many types of environment, many types of system, this correlation time is inversely proportional to the temperature. It's basically the lowest non-zero Matsubara functions for those that you like, those of you that like Matsubara formulations. So the goal is starting from a unitary evolution. This is called the von Neumann equation, and going again to our beloved Lindblad master equation. There are 3 standard steps. The first, and all depend on the existence of a weak coupling. So they're all perturbative, although in a smart way. There's a first step is called the Born approximation, which is related but not the same thing as the one that you do in scattering theory. It means neglecting some of the correlations that you get, that the dynamics induces between environment and system. And the goal of this step is to essentially remove the dependence on the environment, let's say removing the need to track the environment and get an equation for rho s only. Next step is the Markov approximation, which means neglecting Bath memory. As I advertised earlier, if you work out the dynamics to second order in lambda, you get an equation which has symbolically this form. So the rate of change of the density matrix depends on the history of the previous states of the system, weighted by the correlations in the bath. So the bath is providing memory to the dynamics. Now, generally, you don't want to solve these kind of equations. It's a little bit heavy to manipulate. So the Markov approximation is essentially pulling this rho out of the integral and putting times t, so that this is an ordinary differential equation that's easier to solve. Actually, at this point, you would get the master equation that you get as a name is Redfield master equation. Is historically probably the first one to be written down before Lindblad. But as it turns out, this master equation has an annoying property. It does not conserve positivity. You are not guaranteed that if you put a physically admissible state, you would get a physically admissible state. You can get negative probabilities, or worse, everything blows up. So there's a third step, it's called secularization or rotating wave approximation, RWA. And it's a recipe for neglecting some dissipative processes in this equation so that the outcome preserves positivity. And you get, at this point, the Lindblad-Master equation. This probably is the least intuitive of the approximations, and it's always been considered probably the weak point of this derivation. And many people tried and still try to find master equations that avoid this step.
So if I understand, somehow, let's say, you did the first two approximations, fine, but then you realize that you didn't do so well in the sense that you fuck up a little bit the physicality, so you reboot,
Yes.
okay. Yeah.
Yes. They, let's say, the point, these are not, let's say, completely independent approximation. They really fit together by some kind of mathematical miracle. So, yes, essentially in doing these two, approximation, you end up giving too much weight to some processes that then feed back on the eigenvalues and they blow them up. Yes.
Yeah, in some classical systems that I'm used to, you have problems when you treat them in this way, and when you have different orders of limits. And I see here you have like 3 limits essentially. You have lambda to 0, time to large time, so time to infinity, and I guess the environment size to infinity.
Yes, the environment size is usually the very first one. You start from all of this doesn't make any sense for a finite environment.
Okay.
So there are tricks, like mathematical physicists love to scale time and lambda at the same time. And this gives you an impression that, for instance, some will claim that essentially you get rotating wave approximation for free in this sense. I don't believe this approach. It's a nice mathematical device, but it's not what I would expect to see in a lab.
Thank you.
By the way, to be fair, I mean, I am praising the Lindblad-Master equation because it's very used and it's very easy to use. But there are many studies that point out that the Redfield-Master equation, where it works better. But then you pay the price that it's a little bit more complex. You have less techniques that you can use, and sometimes you can get unphysical results. Unphysical meaning something bizarre happens, you get negative probabilities, or everything blows up even.
So you said that, so, okay, I think there's 2 things, right? You said that a Lindblad is the most general way to write down a Markov version of the dynamics.
Which
so
preserve positivity.
Okay.
And positivity, and the relative mass equation is non-positive.
But so, do you get a worse version of the Lindblad-Master equation than the other one whose name I forgot?
Redfield.
The Redfield. Because you do this procedure? Or for instance, if you tried to instead find the best Lindblad equation to reproduce the dynamics, could you meet it? I mean, the point is that there is it's non-Markov? I guess the Redfield is also non-Markov.
No, the Redfield is Markov. Is the one that you get right after Markov.
I see.
I mean, I'm being really qualitative here because the math is involved, and for instance, an easy explanation of why this thing doesn't preserve positivity is not trivial, except for the fact that you see that it's not in Lindblad form. So if it's not in Lindblad form, it will not preserve positivity. But in practice, you can apply it, and sometimes, well, depending on the system, you get meaningful results. This, for instance, has, if you, let's say, in this case, if you choose the jump operators wrong, or you do things a little bit too phenomenological, then it's probably that you're going to screw up in that equation, and you're going to notice. In the Lindblad equation, if you screw up, you don't notice it because the state is always physical. So probably this is going to be more or less my last slide at this point. So essentially all these steps require a separation of timescales. We have 3 timescales with the correlation time for the bath, tau b, which is the time at which correlation functions decaying. Then there is this tau s, which is the inverse of some specific frequencies of the system. I need to be very vague here because it's not obvious it's not super simple to see what is this timescale, but let's say, imagine that the system on itself is a finite dimensional system. Coherent evolution, unitary evolution means rotations. So you're gonna have the components of the state are gonna oscillate in time. And this frequency is related to the frequencies of these oscillations. And then, so these are 2 intrinsic timescales, the bath on its own and the system on its own. And then there is the decay time, which is predicted by the master equation, tau r. And the condition for the validity of Lindblad essentially boils down to the fact that this tau r must be longest. It must be longer than the bath correlation time to get Born and Markov. They usually tend to go together. And then it must be longer than this tau s. So the system essentially must be fast also with respect to dissipation. So it's always, yes?
Tau S and tau B can be whatever they want.
There is no obvious relationship between the 2, yes. And so now I can tell you, when I told the coupling must be small with respect to what? It's an energy. So it turns out that the actual small parameter is lambda times correlation time of the bath. And then it turns out that the linear master equation predicts this inverse square scaling, which generally guarantees that these inequalities are satisfied unless this delta omega or tau b are doing something funny. This quadratic scaling comes because tau r is essentially the one you get from Fermi-Golden rule. One interesting aspect of this is that the coupling is amplified, has to be multiplied by the memory time of the bath. So if the bath has a very long memory, meaning its correlations decay very slowly, you could essentially start with a lambda, which is small in comparison with a bandwidth or the energy of the system. So you would expect weak coupling, but actually the coupling is strong because tau b is big. And if this turns out to be, it's a common route to get strong effective interactions in all areas, not just open quantum systems. If you have very slowly decaying correlations of some kind, which are usually imply the fact that you have soft, very low energy excitation in your system, then probably if you couple to those excitations, you're gonna have an effectively strong coupling. And for open quantum system, it means that generally you break Born and Markov together. I have to insert a disclaimer. I simplified a little bit the things here. If you have power law correlations in the bath, they have potentially a large or even infinite tau b. All is not lost. You can still have Markovian dynamics, but you need to look in frequency. So you have to look at the spectrum of these correlations and see where the system is probing the spectrum. But this is a more complicated situation, which is, however, quite interesting in my opinion. So I think I've been very long, so I'm gonna skip these 2 slides. So I'm just gonna conclude here. I hope this was of interest to you. I try to show you what are open quantum systems, why they're interesting from both a conceptual and practical point of view. I try to give you an overview of the typical approach of quantum optics and/or quantum information that focuses on the density matrix of the system. So you want to describe the full state of the system. And I show you one of the main tools, which is the Lindblad master equation, which is very convenient for all the things that I've said. Other master equations exist. This has to be acknowledged. There's a whole industry of deriving new and better master equations. This is very flexible, very nice, but one must be careful about its limits. If you are curious, read my review. And since in this institute lots of people do more high-energy physics stuff, it's nice to notice that this approach has been pioneered, has been seeping into these more traditionally high-energy physics research topics. You have various flavors of QFT and particle physics. There's a whole book on this. People describing heavy ion collisions with these tools. Cosmology, there are models of inflation which adopt this open quantum system approach, or even black holes, which are definitely open system since they radiate Hawking radiation. And with this, I thank you for the attention.
Thank you very much. We were over time because there were already many questions, which is great. More? Yes, many. Okay.
Good.
Let's go one of the two. Well, students first. Yeah.
Well, thanks for the great talk. I have a question regarding rotating wave approximation. So suppose you have an atom and you put it in an electromagnetic bath. This will result in splitting of the lines with Zeeman effect, for example. And then these lines will have like very small energy transitions between them. So this would affect the approximations you're using, because there's delta omega times tau r.
Yes.
Very less than 1, but this is like a common approach to master equation to deal with these systems.
So technically speaking, there's a range of magnetic fields in which rotating wave approximation breaks down. I'm aware of only one paper in which this has been, done properly. There are, let's say, somewhat easy escape routes to, let's say, still do the, let's say, you can do a partial RWA. So you do RWA where you can, and then you take these almost degenerate cases, and you somehow put them together. So there are simple workarounds. Not all is lost. But yeah, technically speaking, if you just want to have the brutal RWA for sufficiently low magnetic field, this breaks down. In many cases, I suspect that in practical cases, I think that the point is you need to tune the magnetic field to very low values, because generally atomic line shapes are very sharp. And essentially, the criterion is, so you look at the spectrum of emission of the system, and so this is my delta omega, and this is my gamma, which is the inverse of tau r. And if you can resolve the two lines, then RWA is safe. If the lines start to overlap, so you make a prediction, I'm not saying that you look necessarily at the experiment, but if your theory predicts the lines essentially overlap, then you cannot use RWA in its original form. You have to do some adaptations. Mind you that, let's say, if the two lines are exactly on top of each other, so there is no splitting, RWA is safe because you don't need to do it. So if delta omega is exactly equal to 0, then essentially you get an equation, you do all the steps, and you get an equation in which you don't have to do RWA because it's already in Lindblad form. There are situations in which this is relevant, usually not the usual like optical emission of atoms, unless really you tune your magnetic field to reach this regime. But it can happen, for instance, when core levels are involved, because then the decay rate is very big. So it's very easy for the lines to overlap. And then, essentially, well, this case is studied. It's called, you get Fano effects, the Fano interference effect, which is studied, again, with this core, whenever you excite core electrons. There's a whole business. Again, quantum optics people usually know instinctively what to do. There's an easy recipe of going out of this, but outside is not always obvious.
Thanks.
Yeah. I want to know how this methodology of yours connects to the way Caldeira-Leggett did for 3D dissipation quantum systems. Okay?
Yes. So
I mean, I don't know if you connect it or
there's a connection, yes.
I imagine that you do.
So the Caldeira-Leggett model is an excellent example of an open quantum system, and which has been studied thoroughly. And so generally, that model is not Markovian. So that generally, you cannot map it to Lindblad. You cannot expect it to work with Lindblad. There is a limit in which you can make a mapping which is somewhat in Lindblad form. So generally at high temperature, if you have the environment which is very high temperature, you can get something that resembles Lindblad. Technically speaking, the problem is that you cannot perform, let's say, suppose that you have, let's say, really quantum Brownian motion, so there's no potential. You just have a free particle and a bath of harmonic oscillators. Then you have a continuous spectrum. And the continuous spectrum has all these delta omega, which are small. I mean, imagine to have some finite but big confinement, which means that the level spacing is very small. So then, technically speaking, you cannot have Lindblad. You get Redfield. And the Redfield equation for the quantum Brownian motion is exactly one of the cases in which you get everything blows up. I mean, literally, there is a divergence because you get negative rates. But again, at high temperatures, there are some ad hoc ways of reinstating a Lindblad form and getting a good master equation. Vice versa, if you have a strong confinement, then the level spacing becomes big, and you can easily map to Lindblad.
Okay, thank you.
More? Okay, if not, we can thank Martino again.